I didn't get it go. Feel nervous now.
Don't worry, the last one was, the whole end of the last one was just me and Nathan talking.
Okay, so I think the schedule actually said transportation and surveying. I'm going to mostly talk about transportation and surveying. We'll probably cover next week with engineering economy. So if you were planning on skipping engineering economy because it's so easy and you got it the first time through, you can at least show up next week for surveying. And realistically, some of the transportation stuff, especially the geometric design, is consistent. I don't really know whether it's geometric design and it's transportation or if it's actual surveying because it's covered in both sections. So I always start off on the transportation section with this, as opposed to, and maybe I'm a little bit jaded in my opinion because I teach the transportation stuff, but everything that's on the exam that's within the transportation section you've seen in class. So, except for the couple of you who are just now going through transportation for one reason or another. But for those of you who have already completed transportation, you've seen all this stuff in class, and you have the majority of the equations. So I'm going to focus on some of the equations that aren't in the exam, but they're important equations and concepts to know. And kind of the reason that I don't give them to you in transportation class is because you're not going to get them on the FE. So there's some stuff that's kind of knowledge that you need to retain from transportation. But all the problems are workable. You just need to find the right equation. And they also try to trip you up on the units. I mean, a lot of stuff, transportation, miles per hour, feet per second. But for all of the equations, for all the variables, did I give you that part? Yeah, most of the variables they define for you and give you what units they relate to. So you don't have to memorize all the units, you just need to check. And carry your units through on your calculations to make sure that they still make sense when you get to the end of the problem. So what I plan to do is go through the reference manual and show you which equations are important and how to use them. And I think if this is the right one, this is 162 to 168, so it looks like I missed page 162. I don't know what's on page 162. Yeah. Is anybody looking at it? What is it? The variables. Yeah, so you do need those variables. And unfortunately, I didn't print it out, but you'll get it on the actual manual. Sorry. So the transportation topics constitute 12% of the afternoon section of the exam. And I don't remember if this is how I broke it down or if they break it down in the manual like this, but related to streets and highways, you have geometric design, vertical and horizontal curvature, which we covered. Pavement design, we covered towards the end of transportation. We covered one method of asphalt design. If you look on the back of this handout, there are some pages on, like the very last page is on super mix, which is a type of asphalt design, as well as the previous page, page 167, super paved. So those are really like a graduate level course in pavement design, which you get into that depth. I've never talked to any students yet, off the record, I've never talked to any students yet who have actually had a super pave or had a problem on the exam that they had to use one of these last two pages. And I did take a graduate course in pavement design and did learn super pave. And I mean, you might say those problems to the end and go back and see if you can figure it out. I mean, there aren't any special equations. It's more so if I've got these certain conditions, environmental conditions, there's a certain asphalt grade that should be used, or a certain grade of binder that should be used in the asphalt mix design, and that's kind of what this procedure walks you through, is matching the local conditions for wherever that pavement's going to be. So I don't have any examples in here related to those last two pages, but hopefully you won't get an equation or a problem on the exam pertaining to those. So intersection design, really the only thing I want to cover on intersection design is yellow and all red times. I know those are covered to an extent. Beyond that, I don't know. I've never heard of anything else intersection related that's covered. Traffic analysis and control. Just in this version of the manual, I think that they finally add in the traffic flow, the flow rate, speed, and density relationships. That wasn't on the FE when I took it, but those are in there now. And the only equation they give in parentheses, and they hardly give it in parentheses, is the Q equals KV equation. And I don't think I have any examples of that. Actually, I might have a few examples of that. Traffic control devices, I'm not going to cover traffic control devices, but the MUTCD supposedly is on there, but I doubt they're going to ask you to memorize anything. It's got to be just common sense stuff. Same thing with safety. There's not explicit safety. I don't think they give you the equations for calculating rate per million entering vehicles and some of those normalized crash statistics. So I think safety is just kind of an underlying concept in the horizontal and vertical curvature, and we have stopping sight distance. So stopping sight distance equation is kind of safety related, and that is on the page that page 162, which you didn't actually get. So let's start off with vertical curves. So this is the excerpt from the page that you have there. And again, with the vertical curve, we have two tangent sections. We have two types of vertical curve. What are they? Sag and crest. So the crest curve, we're going to have a positive G1 and a negative G2. That would be a crest curve and a sag curve. So we connect those. And the main parameter when we design a vertical curve is the actual curve length L. So we're going to start at VPC. VPI is where those tangents intersect in VPT. So this is vertical point of curvature. And of course they've got them flipped on here, of course. Vertical point of curvature, vertical point of intersection, and vertical point of tangency. The main thing to remember with vertical curves is the length and all x distances are in the horizontal plane. So we don't measure curve length for a horizontal curve along the actual road, along the actual curve or slope of the road. It's all in the x-axis or in the horizontal plane. So it's always good to think about these curves. So you've got kind of your y, you're looking for a y in the calculations, which is going to be an elevation. And then the x distance, the x is going to be the horizontal distance or some station reference. It's safe to assume that all of the curves you're going to see and all the curves we had in transportation, that the relationship from the VPC, or the distance from the VPC to the VPI, is going to be L over 2. So we call this an equal tangent vertical curve, and that's kind of what I've drawn. This is my drawing. I've shown in here L over 2. They don't give you that in the calculation, but 98% of the calculations, you can assume that it's L over 2. The only tricky part, or kind of the only thing you really have to remember that isn't explicit here, is how to, so each of these points, VPC, VPI, and VPT, we're interested in what's the elevation of that point and what is the station of that point. You'll almost always be given the VPI information at the start of the problem. So if they say this is 12 plus 0, 0 at 500 feet, say G1 is negative 0.05, G2 is positive 0.02. So just by looking at this, you should be able to extrapolate up what's the elevation. So if we know what this length is, say 400 feet, we know the x distance here is 200 feet, because this is L over 2. So we've got 200 feet times that grade. Add that to this elevation will give us the elevation of this point. from the station standpoint, 12, if this is a 12 plus 0, 0, we're going back in the X direction 200 feet. So this station is going to be what? 10, station 10, or 10 plus 0, 0, and the end one would be 14 plus 0, 0. So don't go looking for an equation of how to calculate the station and the elevation here. The equations are kind of embedded in here, but they're not really explicit. And so I think it's just easier to look at it and try to figure it out just by reasoning through it. So you do get, this is your main equation here, so finding the elevation on the curve. So that's where you've got the elevation of your VPC, or your starting point, plus G1X, plus this term, which do they reference on here? Yeah, this is the equation for a parabola, and this is that parabolic offset term. So the way I typically explain this, you've got your Y PVC, so this is your VPC, you've got the elevation there. The second term plus G1X, for the X distance, you're just projecting, so say our point, we want the curve elevation there. That second term is just projecting along that first tangent. So you're projecting G1 times whatever your X distance is, and so this is going to keep extending after you pass the VPI. So if we plugged in X, say X in this case was 500, if we plug in, multiply G1 times X, that's going to give us the vertical change from the PVC up to that point. And then that last term is going to end up being a negative in this case, and it's going to drop our elevation back down to the point on the curve itself. So that's the parabolic offset term. So G2 minus G1 over 2 times L times X squared. And do not, I always go through and do these calculations individually because it's very easy to forget that squared term, and it's going to throw your answer way off if you leave that squared term out. But if you go through and compute them individually, you can kind of see if the numbers are at least the same magnitude between each of those terms. The other equation to point out is this first one. This will give you the horizontal distance to the minimum elevation on the curve if it's a sag, or to the maximum elevation on the curve if it's a crest curve. So this is going to give you the X distance measured from your VPC over to wherever that point occurs. Then once you know the X distance, you can plug X into this equation and get the actual elevation of the high or low point on the curve. So like I mentioned before, they're going to probably give you the curve length. You don't really have enough information on the FE. Yeah, I take that back. They do kind of give you enough information to calculate a curve length, but I'll talk to you about that here in a minute. The quickest way to calculate the curve length was that L equals KA method. So K, there's a table, you can look up the K factor depending on what the speed is and whether it's a crest or a vertical curve. They don't give you the K values in here, so you're probably not going to have to use that. But you, on this first page, do have the equations for calculating curve length the brute force way. So if you remember the S greater than L, S less than L, stopping side distance greater than the curve length, you got to go through and do both calculations to see which equality is satisfied. So I think I've got a few examples of that here in a minute. But assuming for the purposes of these calculations, you're given a curve length, they're always going to give you the grades G1 and G2. They're going to give you the VPI, station, and elevation. Even if they don't give it to you and ask you to back calculate them, hopefully you can figure that out. So they're going to ask you to find the elevation of the VPC, VPT, and a point on the curve, the station at the VPC, VPT, and point on the curve, as well as the high-low point on the curve. So again, the biggest mistakes are confusing the units of the grade, percent versus decimal, as well as the distance for the X value using station versus feet. Everything I did in transportation was grades as decimals, distances as feet. I think it's a little confusing working with the percentages and the stations. So if you stick with the decimal and the feet, as we did in transportation, you should be okay. All right, so let's look at an example. We have a back tangent. So what's back tangent mean? So if you're starting at the VPI, looking back to the VPC, that would be your back tangent. So it has a plus 7% grade, and it meets a forward tangent with a negative 5% grade. So is this a crest curve or a... Can I write over here? No, I need to write that. Is that what you're going to tell me?
Yeah.
I need a one of those, see the kids in the mall with the strap on the back and the backpack and they're eating on the key meals. Yeah. Wow. So is this a crest curve or a sag curve? So this is going to be a crest. So we have plus 7%. And minus 5%. The curve length is 1150. That's L equals 1150. We have a BPI of 20 plus 35 and elevation of 250. So first, find the station and elevation of the VPC PVC. So what's our station going to be? Calculation. So 2035 minus 1150 over 2. What's that give you? 14 plus 60, let's go ahead and do the VPT station. That's going to be 2035 plus 1150 over 2.
2610.
So now what about the VPC elevation? So our starting point is definitely our 250 at our VPI. Now are we going to be subtracting this term or adding this term? So the VPC elevation definitely needs to be below. So we can kind of forget about the signs on these because I think that's more confusing. We just know we're going to be subtracting whatever that vertical offset is. So that vertical offset is going to be minus our percentage, our grade, times this distance. So that grade times this x distance will give us the change in y. So we have 0.07 times 1150 over 2. 20 what?
209.
It's a big drop. VPT elevation is also going to be subtracted because we know that elevation needs to be lower. We're subtracting 0.05 times 1150 over 2. Any questions on those? I didn't actually draw a curve. Were you confused?
I do have a question.
Yep.
You said earlier that the back tangent, it's looking from the VPI to VPC.
Right.
So I think if you're looking from there to the VPC and it says a positive grade, then that's going uphill. Because I was thinking of the sag.
If you were doing that though, they would both need to be, you would end up, you were here and it was positive from there, that same thing, you'd end up negative on the other end, right?
Yeah.
So you'd end up.
I didn't try the other one.
Yeah.
Okay, thank you.
So it's usually the first leg of it is given and specified as the first part. All right?
Yeah, he was making fun.
No, it's a good question, because it did cross my mind before. I was just a couple steps ahead of you for once, thinking about what the ramifications were if you treated the negative I that way. Everybody got this? Yeah. So now we want to find the curve elevation at station 21 plus 35. So the first thing we want to know is where on the curve is station 21 plus 35 relative to the VPI. So we're going to be about 100 feet to the right of the VPI. So that is the station we're trying to find the elevation. So what is the elevation going to be? So we've got our Y, VPC, plus G1X, plus G2 minus G1 over 2L. Is that right? Times X squared. I get that right. Okay. So we just calculated the elevation of our VPC. What was that?
209.75.
G1X, so 0.07, and we do keep the signs on our grades in this equation. So we got positive 0.07. What is X?
VPC.
Station or period stuff.
So is it the station?
The distance from
It's the distance.
So it's the distance, assuming that our VPC is an X equals 0.
Yeah, you do 2135 minus the VPC station.
So X is going to be equal to 2135 minus, what was it? 1460. That's going to give you
575. 675. 675. No, I think I'm right. No, you're wrong.
all right.
2135. You're doing 2035. Sorry.
Yeah, so we're using the actual station that we're interested in, so that's going to give us an X distance of 675. So plus, so G2 is negative 0.05 minus 0.07 over 2 times 1150 times 675 squared. So keeping those terms separate, 209.75, what's 0.07 times 675?
47.25.
What is it?
47.25.
What's the last term?
Negative 23.77.
23 point.
77. Could you use black?
If I've got one, please.
Please. Per request of Professor Humphrey. That'll work.
All at once?
Yes.
Okay, so these numbers are at least relative. They're not off a magnitude. I mean, if this was 209 and this was 472, that might raise some flags. So they should all kind of be relative magnitude to each other. So what do these give you combined?
233.
Even?
0.23.
Mark, I got some grip on it. So what's happening here, we're starting off at 209.75, so we're going up 47.25, so we're actually projecting to here. So this point is 47.25 above, and then this last term we're coming down 23.77. So that's the way that the parabolic equation works. Questions on that? So, yeah, curve elevation is all we're at. Everybody got that? So next we want to find the station and elevation of the high. Oh, I remember what I was going to ask. So critical thinking, what do we know? What are the extents of this number? We know it has to be greater than what and less than what? So it definitely has to be greater than both of these elevations, and it has to be less than our 250. So you always have some boundary there for reasonableness for your answer. Station and elevation of the high-low point. So we're going to find a high point or a low point?
High.
So our x distance to the high point is G1 times L over G1 minus G2. So again, keeping the signs, 0.07 times 1150 divided by 0.07 minus a negative will give us a plus 0.05. So what's that give you? 670.8. So we left of the VPI or right of the VPI? So we're going to be slightly right of the VPI, and we're actually pretty close to our elevation we just found because it was 675. So now we can find the y value using the same equation that we did before, 209.75 plus 0.07. Now plugging this value in for x, 670.8 plus, you guys can figure it out from there. So the only thing that's changing is now we're plugging in the distance to that high point that we just calculated instead of 675 that we had before. And then the station, you can just add that to whatever our VPC station was we calculated before and find out that that station was 21 plus 30.8 or something like that. The station of the high point. So questions on vertical curves?
So we found the horizontal distance in the x high.
Mm-hmm.
If we add that to our VPC, would that be the station of our high point?
Yes, if you add the VPC station. Yep.
Okay.
I just got the same exact answer as our y elevation earlier. Finishing out that equation.
With 670.8 in there instead of 675?
Yeah. I don't know how that happened.
Wow, I got pretty close. It's not exact, but
Yeah, so it might, I mean, on a curve of 1,150 feet, we're only looking at a 4-foot difference, so you're looking at very minimal difference. You must spit the number out. All right, everybody ready to move on? You guys want to figure that out?
No, I mean, I've answered it, I believe.
What'd you get? 233.229. What was the last one?
I got the same.
it was 0.228 last time.
Okay. Very little. 4 feet. All right, so horizontal curves. I think I've got 2 slides here. So horizontal curve information takes up page 164. So this page has all of the definitions, so they correspond to the diagram. The only thing we're doing with horizontal curves is dropping the V. So same concept, we have a point of curvature, we have a point of intersection, point of tangency. Main difference here is that the length of the curve, which is L, so the main thing to confuse if you're in a hurry is length of curve with long chord. So length of curve is L, long chord is C. The difference is long chord is the straight line distance connecting the PC and the PT. L is the length of the curve, which is actually measured along the center line of the roadway. So most of the calculations and most of the time we're interested in L. So with horizontal curves, we want the distance measured along the center line of the roadway. So the main thing that they do not give you in terms of the equations, which is a basic relationship, again, you're going to be given the initial PI station and asked probably to find the PC station and the PT station. T is the tangent distance measured from the PI to the PC. So if you're calculating stations, we always start at the PI, and to get station PC, we just subtract that tangent distance, which I've shown here. So this isn't on, you're not going to get this, but you need to remember this for the test. So to get the PC station, we take PI minus T. Then you get the PT station, we take the PC and add the curve length along the center line. So you cannot take the PI and add the tangent distance to get that PT station. You have to go back to the PC because we want the stationing along the center line of the roadway. For roadway construction, we need that reference to be along the center line. And if you just take PI and add T, that's basically assuming that this distance is the same as this distance, which it's not. But if you were plotting coordinates, so if you knew latitude, longitude here, latitude, longitude here, and you were trying to find latitude, longitude here, calculating latitude, longitude, you can get the same answer by doing both of those calculations, but that's not what we want. We're just setting up the referencing system along the center line of the roadway. So you have pretty much every equation you could possibly need on this list, so it's a matter of figuring out what's your known information and what's your unknown information to calculate whatever you're looking for. So a horizontal curve is laid out with the point of intersection at station 22 plus 0, 0. The curve has a radius of 1,000 feet and an intersection angle of 120 degrees. So looking back here, intersection angle is basically how far is the curve lasting from the PC to PT. So if you have a small intersection angle, it's a really short curve. If you have a larger intersection angle, you're going to have a much larger value of I, that intersection angle. The radius is what is controlling how sharp the curve is. So if you have a really sharp curve, are you going to have a small radius or a large radius? Small. You're going to have a small radius because the larger it gets, the closer it gets to infinity, which is a straight line. So whenever you're doing curve design from a safety standpoint, obviously the larger you can make the radius, the better, because that's going to be a gentler curve and less likely that somebody's driving too fast going to slide out of the curve. But generally making a larger radius is more expensive because you're going to have to take more right of way. We've got an intersection angle of 120 degrees. The radius is, so some here out in is the center of the curve and the start of the radius, and it's usually not within a reasonable distance of the intersection. In this case, it's 1,000 feet off. So instead of planes, you're generally not going to see back to the curve. So we always work left to right. So PC, PI, and PT, that's radius is 1,000 feet. And our PI is at station 22 plus 0, 0. So first we want to find the degree of curve. So basic relationship, you're either going to be given a radius of the curve or the degree of curve, and this equation up here allows you to go back and forth between the two. The degree of curve is defining what's the total angle that's turned. So if you look at 100 feet along the curve itself, what's the total angle that's turned in that 100 feet? It's just kind of a standard that's used to define how sharp the curve is. But it's all based on 100 feet out here on the arc. So we can calculate the degree of curve, 5729.58 divided by 1,000. It's going to give you 5.729, depending on how many decimals you want to take, 0.296 degrees, or hopefully everybody remembers how to convert to degrees, minutes, seconds with your calculator. That might come in handy on the exam, both possibly for this section, but definitely on the surveying section. Does everybody, let's go ahead and convert this. What is this in degrees, minutes, seconds, to make sure that you do know how to do it?
43 minutes. 46.49 seconds.
What is it?
47 seconds.
Does everybody get that?
Yep.
I didn't round that far.
It comes down to seconds, but.
Yeah, seconds are super accurate.
That's the beauty of the FE and having multiple choices.
Yeah.
So that's the degree of curve. Now what's the tangent distance? So these horizontal curve problems are pretty much going and finding the right equation. So tangent distance, which equation is the best, easiest? T equals R tan I over 2. So this would be 1,000 times the tangent of 120 over
1732.
what is it?
1732.05.
Find the length of curve. Again, the biggest mistake to make here is assuming the length of curve is LC and picking the wrong equation. And I guarantee that'll be one of the possible answers on the multiple choice. So length of curve, we're looking for L is equal to I over D times 100. Might not be able to hold up the black marker in the black. I over D times 100, 1,000. So 120 over 5.7296.
2094.
2,000.
Yeah. 94.
So again, kind of common sense. I mean, all these numbers should be relative magnitude to each other. And then finally, the PC station and the PT station. So PC is going to be equal to what? So 2,200 minus T, that I just erased. 1732. What's that give you?
468.
What is it?
4 plus 68.
4 plus 8. And then PT station is going to be equal to what?
39 plus 32.
468 plus what? Oh, you're ahead of me. So what do we add to this? 468 plus what? So our curve length, 2094. Which answer was it?
39, 32. That might not be correct. So why can you do PI minus T equals PC, but not PI plus T equals PT?
Because we need the stationing reference along
the center line.
the center line. Good. So the other pieces of horizontal curves are the superelevation. Also, I don't know if that's as big of a deal with degrees versus radians, but you're going to be using trig functions to make sure you're in the correct mode. But superelevation, you get this section. This should be on page 163 of the, yeah, on that front page. This is for designing horizontal curve, or sorry, for designing superelevation. Yeah, I've got an example on the next page. The spiral transitions. Who remembers what the spiral transition is used for?
Gradual.
Exit ramps.
Well, the gradual transition between curves.
So they are used in exit ramps, but they're basically to provide a different type of transition, as opposed to having a straight line segment and then instantly having a PC and starting that curvature. You can go in and add a transition section to where it's almost impossible to draw. So let me. It's actually a transition section where the radius goes from infinity to match whatever the radius is of the actual horizontal curve. So if you're the driver, if you're driving with a spiral transition, as you enter the curve, you're going to be able to slowly and gradually turn the steering wheel. And then once you get to the PC, you should be able to hold your steering wheel there while you continue through the rest of the curve. If you don't have a spiral transition, you're driving on the straight line segment. As soon as you get to that PC, you've got to almost instantly turn your steering wheel to match it. So that's the difference. And really the spiral transition is, we have that because of the railroad industry. If a rail car or a train is going around a curve, it can't instantly adjust itself to follow this track. So the spiral transitions are necessary in order to, so the train doesn't jump the tracks. So just in case they ask you, so this is based on the velocity, the radius of the curve. So this would be the radius of the curve you're trying to match. And then C, that they say you use 1 foot per second. This is the rate of increase of lateral acceleration, which is as that car is making that turn, what's pushing out on it. So C is assumed to 1. You've got all the information here if they want you to calculate that spiral transition length. So the length you calculate is going to be basically from infinity, however long that needs to be, however long that transition section needs to be. All right, so super elevation. 2-lane railroad has a 10-degree horizontal curve extending for 750 feet along its center line. The road is 20 feet wide with 2-foot wide shoulders, and the design speed for the road is 50 miles per hour. So the actual equation for super elevation, 0.01 E plus F is equal to V squared over 15R. So those of you who still have the first section, or page 162, what are the units that it specifies for V?
That equation is almost.
Miles per hour.
Oh, the units page. I'm sorry. I didn't listen to you.
What is it?
Miles per hour.
All right, so V is supposed to be in miles per hour. What is R supposed to be in? Feet. So this 15 already has a conversion factor built in to go from miles an hour to feet. What is this value F? So this is the friction factor. What are the units? None. What about E? What are the, what's that percentage? So the only thing that's happening here is that you're taking an E in percentage and turning it into a decimal format. So the way this equation works for superelevation, if you've got a car or something that looks a lot like a car, it's supposed to look like a car.
Wheels, I like it.
It looks like a spaceship. It's like you want jets.
It's a really cool hovercraft.
I've never claimed to be a good artist. So if the car is driving in and out of the road, the superelevation, the value E, is basically what that internal angle is there. So the higher your superelevation is, the higher that banking is going to be on that curve. What's a typical superelevation amount?
3.
So 3, 4, we very rarely see anything greater than 5 or 6 unless it's like a NASCAR track, and their super elevations get to be up to what, like 18, 20%? So depending on the track, they're pretty high. Are they? 31? You're like climbing up the, and actually on, what was the movie? With Ricky Bobby, like out there, kind of see you climbing, trying to get up the track. Anyway, good sidetrack. So you can kind of view this as an equality. So these two terms, both the friction of the pavement as well as the superelevation, are holding the car in the curve. The speed and the radius are pushing the car out of the curve. And so as long as this side is greater than this side, you should be okay, because the forces holding the car in the curve are going to hold it there. If this is less than this side, then that's when the car is going to spin out. So if we have, got to remember what the problem is now. 2-lane rural road with a 10-degree horizontal curve extending for 750 feet along its center line. The road is 20 feet wide with 2-foot wide shoulders. The design speed is 50 miles an hour. Find the superelevation needed on the curve to give a side friction factor of 0 at the design speed. So we're assuming that the side friction factor is going to go to 0, and we need to solve for superelevation. So I'm going to drop this and just assume that the superelevation is going to be in a decimal format. So what's V squared going to be? What's our value for V? So we got 50 squared over 15, and what is R?
10 foot 12.
What is it?
12. That's wrong.
That's a 12-foot.
Is it the radius of the curve?
So R is the radius of the curve.
So then we have to actually go through.
So what do we have that will allow us to find the radius of the curve?
L.
We have L and the degree.
So we have a 10-degree horizontal curve, which is what value? What is 10? That's our D, so that's our degree of curve. So we should be able to find R by 5729.58 divided by D, which is 10. This will give us a radius of 572.96. Everybody got an answer?
So that's how they would say D was 10 in words.
Yeah, so it's a 10.
That's fine.
It's open mic. Yeah, a 10-degree curve.
Yeah.
I suppose, so it couldn't be a vertical curve, because we're going to talk about vertical curves in terms of degrees. Slipperiness.
Slippiness.
Anybody get an answer here?
2.29.
What is it? That's a lot of super elevation.
Must be an X right there.
Well, that's assuming you got like a roadway price. And they're going.
Then, so if we take the 0.01, we divide by it and we get this 29%. The only thing it's doing is taking a percent and converting it to a decimal.
So it's 50 miles an hour.
No, the conversion's built in. So since it's telling you V needs to be in miles per hour and radius needs to be in feet, so just giving you this equation that is already built in. Now, if it said V needed to be in feet per second, then you have to do the add the conversion in. So that's a lot of super elevation needed, but you're right. So you're going to have some side friction in reality. Stopping sight distance. So this is on, I think, page 162, which you don't have. So this is the distance that a car travels while a person is making the decision to stop. So as you're driving down the road, you see a deer in the road. As soon as you see that deer, you start reacting. So that's why you're making the decision to hit the brakes. That's the first component. Then the distance traveled while you're braking, so the braking distance. And that's more based on what's the grade of the roadway, as well as the friction with the pavement, as well as your initial travel speed. So we can apply this on a straight and flat road. We can apply it on a road with a grade. And it also comes into play on horizontal and vertical curvature as it relates to sight distance and curve length design. So this is the equation that's on page 162 that you don't have in your handout, but it is in your book, as well as all the reference variables. So this S is going to give you the stopping sight distance in feet, 1.47. That's our conversion factor to go from miles per hour to feet per second. So V again is in miles per hour, so this is converting it. T is in seconds, and the normal assumption, or the assumption we use for design purposes, is 2.5 seconds. So that's basically saying if you're driving down the road half asleep and a deer jumps out, it's going to take you on average 2.5 seconds to see the deer, realize you need to hit the brakes, and actually start applying the brakes. So this is just giving you a distance, so taking the speed at which you're traveling times the time over which you're reacting. That's going to give you a distance while you're reacting. Second term, you're going to be taking your distance or your speed, dividing by, this is kind of relating the friction between the friction or a deceleration rate when you slam on the brakes. And again, this stays in miles per hour. Your conversion factors to go from miles to feet, because this term is also going to end up being in feet. It's the braking distance. So the conversion factor is built into that. If you have a grade, then you can adjust it plus or minus the grade, and the grade needs to be in, so it said percent divided by 100. So you plug the G in as a decimal format in this equation. Does everybody remember this equation? How to use it? So the following design requirements exist for a section of highway with a 1.5% grade. We have a design speed of 70 miles per hour, assuming a different driver reaction time, and they like to do that on the FE, give you different values for what's supposed to be assumed. If the driver reaction time is 2 seconds, the driver eye height is 4 feet, and the object height is 6 inches, what is the design stopping sight distance for this section of highway? So based on this equation, we have a little bit of extra information that's not relevant for this problem. That would be the driver eye height and the object height. Those don't come into play unless we're doing vertical curvature design and looking at the length of a vertical curve. So this is just a 1.5 section of roadway that has a flat grade. So the stopping sight distance, S or SSD, 1.47. What's our speed? 70 miles an hour. Our reaction time is 2 seconds plus 70 squared over 30. And A in this equation is the deceleration rate in feet per second squared. They're probably going to give you a value to assume in the problem, but for design purposes, we assume 11.2 feet per second squared. So that'd be 11.2 over 32.2.
Is that 11.2 in the reference?
No.
Nope, I've written it in red. So this I've added and this I've added. These are just kind of the standard values. So for the grade, should the grade be positive or negative?
Didn't say.
Well, it's not negative.
It's one set.
Do you can see the worst case scenario?
So what is the worst case scenario?
Scenario, you go down.
Worst case scenario would be downhill. So the answer is depending on which way you're driving. Are you driving in the uphill direction or are you driving in the downhill? Because if it's a flat grade, you're going to have traffic going both directions. So the worst case scenario would be the downhill scenario because they're going to have, their gravity's helping them go down the hill, so gravity's going to carry them farther. If you're traveling up the hill, gravity's going to help stop you. So we're going to subtract the grade. Again, it needs to be in decimal. So that'd be 0.015. So give me each term individually. It's 1.47 times 70 times 2.
102.9. Oh, not times 2.
205.8.
And then what's the second part?
$4,907.
Sounds kind of high.
Yeah.
I got 490.7.
Throughout 30.
So then together it's 696.5. So if they ask you in the question, what's the distance traveled during perception reaction, that would be the first term. They might even ask you what's the braking distance alone, and that would be the second term. So you could potentially see any one of those variations.
Design purpose, you run it up to the whole number, right?
Yeah. Or the nearest 5. Increment of 5. Questions on stopping sight distance? So we can apply stopping sight distance on vertical curves where you're looking at designing the actual curve length. So again, the longer the curve length, the flatter that curve's going to be. The shorter the curve length, the kind of sharper that's going to be, and the harder it is to see. So we're always trying to design what's the minimum curve length. What's the minimum curve length we can get away with and still provide the necessary stopping sight distance. So that's illustrated for a crest vertical curve. You're trying to see over the hill. For the sag vertical curve, really the controlling condition is the nighttime, where you're kind of restricted by how far ahead your headlight beams are going to illuminate the roadway. Because obviously in the daytime, unless there's like a bridge structure or something actually blocking your line of sight, you should be able to see as far as the uphill goes. But at night, you can only see as far as your headlight beam. So the equations here on this first page, page 163, these are the equations that allow you to calculate L, the length of curve for the vertical curve problems, given if it's a crest vertical curve. So we've got the crest. If you're given, so H1 is the height of the driver's eye. So for this scenario, H1 is the driver's eye height. H2 is the object height. So the default values are 3.5 feet for the driver's eye height and 2 feet for the object height. If you're given different values of H1 and H2, you can use these two equations to calculate the curve length. But if you're told to use the standard criteria, they've already plugged in those values for H1 and H2 and simplified the equations. For the sag curve with the headlight criteria, they don't give you this equivalent where you can plug in the values for headlight height and headlight beam angle. They've already plugged in the standard criteria there. So these are the two equations you have to use. So in those equations, it's going to give you length of curve in feet. S is what we just calculated, stopping sight distance in feet. A is the algebraic difference in grades. So A is a whole percent. So you're just looking, so if you have a +4 and a -3, the algebraic difference is going to be what? 7. So it's the total change in grade in percent. So there's two, whenever you go through these calculations, there's two scenarios or two equalities that have to be evaluated. One where the stopping sight distance is less than the curve length, and the other where the stopping sight distance is greater than the curve length. So only one of these equations should hold true, but it's recommended to go through and calculate both just as a check of your own answers, because I guarantee you the multiple choices, you're going to be given both of them for the correct answer, but only after you determine which equality is satisfied will you know which one of those is the correct. So these are given on the FE. This is for designing your minimum curve length for a sag curve based on riding comfort. And I think this is really the your stomach dropping scenario. If you're going down a curve too fast, you don't want it to you don't want to get that roller coaster sensation. So knowing A and the design speed, that will give you that minimum curve length. This one, if you do have that sag curve where you might have an overhead structure that could limit your sight line, that's what these equations down here are for, where C is your vertical clearance from the midpoint of the curve, or within 200 feet of the midpoint of the curve to the bottom of that structure. So you can plug in C as well as your values for H and calculate the curve length from that perspective. Again, I've never talked to anybody that's had either one of these two on the FE exam, but it's possible that you could get some of this. So you should have enough information to find S, the stopping sight distance, and then you can plug in S and A and the values for H and come up with the L. Again, solve for both equations and figure out which equality is true. So we have a crest curve on a section of highway that consists of a 1% grade followed by a -3% grade with these design requirements. Find the minimum required length of vertical curve needed to satisfy the design stopping sight distance. So we had +1, obviously not the scale. We've got a curve and we're trying to find what's the minimum value of L that we can have in this situation. So looking at our crest vertical curve equations, do we have different values of H? So we've got a different driver eye height and actually it's the same object height. No, actually it's a smaller object height. So we've got to use the first set of equations. So for the condition where S is less than or equal to L, that L min calculation is going to be AS squared. So what's A? 4. So it's going to be 4, not as a decimal, but as a whole percentage. S squared, we know. Yeah, so we're given stopping sight distance in this case is 1,000. So that's going to be 1,000 squared divided by 100 times the square root of 2 times 4. Thank you. on there, it says that the values of H should be in feet. Is that on the first page? Just say H is in feet.
Yes.
Close parentheses. No, don't forget your square. You can ask a question.
I did, you didn't look back.
You didn't say it loud enough because I didn't know you asked the question.
25.
So
6 inches, not
6
6
inches.
feet.
So H2 is the object height of 6 inches, so it needs to be in feet. Anybody have an answer?
97, 1,000 square.
Yeah, no, it's like 27, 29.
That's what I got.
I got 10.
No, that's not right.
Yeah,
What is it?
2,729.
Good curves.
I forgot what
So is this equality satisfied?
Yes.
So S of 1,000 is less than L, so I would say obviously it's satisfied, but just to check, so Eli would have then gone through and calculated the other one, and the other one probably wouldn't have been satisfied either. So then you go through L min, 2 times 1,000 minus 200 square root of 4 plus square root of 0.5 squared all over 4.
1633.
So 1,633 feet, so obviously 1,000 is not greater than that, so that one doesn't hold true. So then we have a little more confidence in this one. What's that?
Then what would Eli done?
Yes.
Like, well, he would have known, well, he would have known, because this one wouldn't have been true, because the 1,000, because you said, what, was 900 something? So neither one of them would have been true, so he would have known there was a mistake in one of them.
Sure. I got 1,007.
For this,
No,
Still true.
One above, yeah.
Well, good luck.
I got
1
272.
versus,
It was lucky.
other than calculator problems, any questions on this problem? So evaluate the stopping sight distance on horizontal curves. Here we're interested in determining, do we have any roadside obstructions that prevent us from being able to see around the curve far enough to stop in time. So this equation, this HSO is the horizontal sight line offset. And HSO, you don't get a diagram on the equation sheet, but it's measured from the I believe it's from the center line of the controlling lane, which would be the inside lane of the roadway. And we're not really given any conflicting or supporting information here, and really the only difference there is 6 feet. So you could go through and do the normal 12-foot lanes. The difference in that is there should be 6 feet unless it's a multi-lane roadway. But yeah. I don't know. I'm pretty sure it's to the center line of the controlling lane. It is? Okay. But that's assuming that I told you correctly, the transportation center. So we've got the radius of the curve here, as well as the stopping sight distance around the curve. So if we have our 2-lane road, again, that has the 10-degree horizontal curve for 750 feet along the center line. The road is 20 feet wide with 2-foot wide shoulders. The design speed for the road is 50 miles an hour. Find the required horizontal sight line offset for this curve so that the trees can be removed from the edge of the road. HSO, the radius, did we have a radius?
Oh, yes.
Okay, so what was it, 5'7"?
It's going to be the same.
5'7"
0.6.
So 5,700.
But the HSO is not looking for the radius.
So I'm skipping a step. So the radius is 5,729.58 divided by 10 from a couple problems ago.
I
So
agree.
that gives 572.96.
I just didn't realize you weren't finished writing. I thought that was it.
No. All right. So we've got the radius now. 1 minus the cosine of 28.65. Do we have an S? Now what do we do? How can we calculate it?
We have to go.
It won't make slides.
1.47 times 50. What's our standard?
2.5.
2.5 plus 50 squared over 30, 11.2 over 32.2. Do we have a grade?
It's a.
We don't have a grade. Trying. What's that?
So is it actually if you go back and calculate
I doubt it.
4.3.
That's pretty complex. What?
4.3, 4.3.
So we plug that 423.3 into stocking site distance and divide that by our radius again at 572.96.
Thank you.
Did you hear anything?
What's that?
We have the answer.
It's 38.66.
So those of you watching at home, sorry, I just now switched to a really dark marker so that you can finally see.
We already had a 5 pages. Should actually be clear.
That is a good point. So the radius of a curve, this is to where?
It's a center line.
This is to the center line of the roadway. So if we want, so the total road's 20 feet wide, so how wide are the lanes probably? 10 each, so technically we probably should have subtracted 5 feet from that to get to the center line of the controlling lane. So that would change those two values and that would be slightly different. I don't think they're gonna get that technical on the exam.
They're like a corner thing.
What's that?
38.99. There was.
Probably say it's most nearly.
Yeah, most nearly 40.
I don't know that they'll go down to the 0.3 for the difference. Good. Or guess C. Unless C was like way different order of magnitude. So traffic flow, you guys need a break? You guys want a break or are we good?
Drink coffee, slip in your head.
Okay. Okay, I'll make down, breaks over. Traffic flow relationships. So this is the speed, density, volume, density, speed, volume. And I still haven't heard from anybody what type of questions they actually ask on the FE exam. But just to remind you of the logic behind these. So when you're looking at speed, density, this is the base relationship. So with very low density on the roadway, what's the speed condition going to be? They're going to be really high. So as your density increases, what happens to speed? And when you're at your max density, your speed is basically a parking lot. So you've got a free flow speed, U sub F, and a jam density, K sub J. And so that is this relationship here. When you're looking at the relationship between volume and density, so when you have no density, you're not going to have any volume or any flow rate. So as the density increases, so does the volume on the roadway up to a certain point, which is the roadway capacity, which is also Q max. This is an equation they don't give you, but you have enough information here to kind of figure out what that is equal to. So once you reach the capacity, if the density keeps going, your flow rate starts decreasing because traffic flow is breaking down and vehicles are slowing down up until the jam density where it's a parking lot, you don't have any vehicles passing by. So that's why you kind of have that maximum relationship. Same thing over here. So with very low volume, very low density, you start out at really high speed. As the density increases, your speeds are going to be impacted up until kind of this midpoint density. Then your speeds are going to continue decreasing, but since the traffic's not flowing, you're not getting any volume either. So hidden up here is the basic equation. Flow rate is equal to density times speed. Q equals K V. Units on flow rate are vehicles per hour. Density is vehicles per mile or per distance. Speed is miles per hour. So our units, the miles will cancel and we're left with vehicles per hour. So a lot of these relationships, just maintaining your units, you can go through and do the calculations. So based on this relationship and what you see here and what you're given, how would we calculate Q max? How do you calculate capacity?
What is the density?
Half of which
It's
density?
half of both, actually. Half the density and half of the speed.
So you've got if we call this half of the total density, or the maximum density, which is jam density, K sub J over 2, times the speed at which capacity occurs, which is U sub F over 2, free flow speed over 2, that gives you KJ U sub F over 4. So if they ask you to calculate capacity, just with this relationship and being able to see here that the capacity occurs at half of the max speed and half of the max density, you should be able to calculate that. The mean speed on a road is given by the relationship V equals 60 minus 0.2 K. So which relationship is this? So this is our speed density relationship, and if you recall from transportation, you could find that if you were given a bunch of data points, you could find that through regression analysis, fit a line to that data. So V equals 60 minus 0.2 K. If the mean speed on the road during rush hour is 45 miles an hour, find the density of vehicles on the road. So how do we do that?
Plug it into the formula.
So you can take the speed of 45 miles an hour. This is more of an estimate because, like I said, this is derived from other data. This equation is usually derived from other data. So if you plug in v equals 45, you can solve for k, which would be, what is it? 75 vehicles per mile. So we can do this without using this relationship. If we were given enough information to solve for an actual flow rate, we can take that speed and the current flow rate and calculate what that density is using this relationship. So how can we find the maximum capacity or that Qmax? Qmax we know is U sub F, K sub J over 4. What's U sub F? So we know that this line is going to intercept at 60. So we got 60. What's K sub J? So when V is equal to 0 down here, we can plug in V for 0, solve for K. That will give us our jam density of K sub J. So 60 divided by 0.2 is, what is it? We'll be close to the
4,500.
What is it?
4,500.
4,500 units vehicles per hour. 4,500. If you can't see that, come ask Matt Newland. He's got it written down. Hopefully we'll be here.
Just text him, his phone number is.
So any questions on traffic flow? So intersection design, are these equations on page 162? Yes. So this is yellow interval and all red interval calculations. So for calculating the yellow interval, you're taking driver reaction time. For a signalized intersection, we use 1 second instead of 2.5 seconds. Who remembers why we only use 1 second, and stopping sight distance we use 2.5 seconds?
To be considered.
Are you expecting it?
Yeah.
Expecting it to stop.
So if you're approaching a signalized intersection, you should be expecting to stop and being ready to hit the brakes, as opposed to on a rural location and a deer jumps out in front of you, you don't expect to have to stop. So we can allow a shorter reaction time for the yellow interval. So here we now have a lowercase v. So here for the lowercase v, we want this in feet per second. Yeah, vehicle approach speed in FPS, feet per second. And our T is in seconds, so our yellow time we're going to end up having in seconds. Deceleration rate here is the same as what we use for stopping sight distance. That's kind of a comfortable deceleration rate without skidding and making black marks on the road. Plus or minus 64.4 times G. So if we have a grade, we will take that into account for the yellow calculation. So the all red interval, so what's a reasonable yellow, or kind of a range of reasonable amounts for the yellow interval? 2 to 5. So somewhere in the 2 to 5, 6, maybe even 7, really probably 2 to 6 seconds. Anything that you calculate outside of that boundary is not correct. And if it is a correct answer, then whoever the transportation person is that writes the FE exam should be removed from their duty.
You'll take it, right?
So the all red interval, we're taking into account the width of the intersection. So the yellow interval is for the vehicle that's approaching the intersection, the light changes, giving them enough time to comfortably come to a stop. So that's how long we want the yellow interval to be. The all red interval, this is assuming once that car crosses the stop bar and enters the intersection, how long do they need for their back bumper to clear the intersection. So this is the total distance they have to travel across the intersection, the actual width of the intersection plus the vehicle length, and you're dividing by the speed at which they're traveling in feet per second. So this is going to give you your answer in seconds. And here's my ever so wonderful and long-living animation.
He doesn't have square wheels.
Ooh, looks like the front of his wheels kind of disappeared there. He's driving so fast, it's like you can't even see it.
That's an Edison car.
I wonder what happened. So let's calculate what the yellow interval. So yellow interval, we've got 1 for the reaction time. Our speed was, what, 40 miles an hour? So how do we convert that to feet per second? So we need to multiply this times 1.47 divided by 2 times 11.2. And do we have a grade? We don't have a grade.
That's 3.6.
So if we calculated this, should this answer be rounded up or down?
Up.
So we always want to round this up because a yellow interval is something we don't want to really compromise on. So we don't want to round it down and short the amount of time that's necessary. So both of these values, the yellow and the all red time, should get rounded up. So for the all red clearance interval, our intersection width in this case is 72 feet, plus our vehicle length, and were we given one?
Nope.
Is that in the book, or did I write that in?
You put it in.
Yeah. So typical length is 20 feet. They'll probably give you a length in the problem. 20 feet, and then again divided by 40 times 1.47. Really?
1.56.
Okay. So 1.6 seconds. So reasonable range for all red, 3, somewhere from 0 to 2. Unless it's a really big intersection with a low speed, you're probably not going to get as high as 3, but it's possible. Everybody see
Really
it
less
across?
than 1 second.
That's at 1.6 seconds.
I said, would it really be less than 1?
It could be. I mean, if you have a really high speed and not a very long intersection, I mean, it could get down that low. But if you're that low, you're probably going to round it up to a second anyway.
It says to round it up to 0.1. Yeah, I think it's red.
In the direction.
0.1 seconds.
Did I have that, or did it say that? Yeah, so make sure you round, and you do calculate it to a tenth of a second, because the traffic signal controllers will take it to that level of precision. All right, so pavement design. Anybody want to teach this second?
No.
I'm the one for president.
There's only one question. We can guess that.
All right, so pavement design, I mean, it is easy. It's definitely going to be easier than some structural analysis problems. So this will be easy points. And we still got 15, 18 minutes. So from transportation class, we talked about 2 components of pavement design. One of them is calculating the easels or the LEFs, which is what the Yeah, on page 166, load equivalency factor. This is essentially the same thing as an ESOL, which the ESOL calculation was one that was in transportation class. So for an axle of a given weight, number of pounds, how much damage is it doing to the pavement? That's essentially what we're calculating. What are the units of damage that are being exerted to the pavement? So the two components do not get merged together. So you have the actual traffic load, and then you have the design of the width or the depth of the pavement based on the material properties, and the ESOLs or the LEFs go into that equation, but within the FE you're not going to get to that level of detail. So they're kind of two separate analyses that you're likely to see. So that load equivalency factor is the first half. The second half is what's the structural number of the pavement, and the structural number is kind of the measure of strength, and it's based on that layer thickness as well as the strength of the layer. And it's assumed that for asphalt concrete you're going to have a subgrade, which its depth is infinity, then you have a subbase, then a base, and on top of that you have your asphalt or your concrete. This structural number calculation will apply to both asphalt and concrete pavements. So all of the information is contained here on this slide. So up here on the top right, you have the structural number equation from the AASHTO method, and we did use this in transportation. We used the nomograph in transportation, didn't we? So after you use the nomograph, you use the nomograph to get the structural number. That was the output of the nomograph. Then you could go and find these strength coefficients from other tables. The depth is in inches. That's the thickness of each layer. And so the layers all interacting together have to provide the overall necessary structural number for the pavement. So the only thing to point out here on this table, these are pounds going from 1,000 to 40,000. This is just continuing on. So this is kind of, they had room on the page. This technically should be placed underneath here. So we got pounds. So we got the load equivalency factors for single axles as well as tandem axles. So calculations. First one using the structural number. We have subgrade, subbase, base, and then in this case we have our asphalt. So each of these have a coefficient, A1, and so we always number from the top with the asphalt layer being A1, A2, A3, and A4, which actually we don't have a subgrade strength. So we just go 1, 2, 3, 4, and then we have the depth of each of these, D1, D2, and D3. So in this case, we are told we have these different minimum thickness amounts and the strength coefficient for these different layers, and we're told to design what is the required thickness of the subbase. So why do we already have an answer there? Oh, these are minimum thicknesses. Okay. So a flexible pavement system, hey, it's been a year since I looked at this. Flexible pavement systems be designed using the AASHTO structural number design method with the following criteria. If the minimum thickness of the surface and base are used, what is the required thickness of the subbase? So we're going to stick with the minimum here, and we're going to solve for what this needs to be in order to provide the design structural number. So this is for the overall pavement depth. So the structural number equation, so we got 2.5 is our actual structural number, and then we're just going to take A1 times D1, which is going to be 0.44 times 2. So that'll give us the total strength of that layer. And we've got 0.25 times 4.
So that's what we're solving for.
We're solving for subbase,
Oh.
so the third one. And then plus 0.10 times D3. So we can solve for D3.
6.2.
6.2 inches, and we could probably round that up to 7 inches. It's kind of hard to get to decimal inches when you're dealing with aggregates and gravel and things like that. So this is, and I really don't know how they could make this any more complex. I mean, the only thing they're giving you is this structural number equation. So as long as you kind of understand the concept of what's going on here, they're going to give you probably enough information and one unknown, and you just need to solve it. Question? So the last one, is this the last one?
Yeah.
Let's do it left-handed to drag it out. Calculate the load equivalency factor or the ESL of a loaded Class 9 truck that has a front single axle transmitting a force of 10,000 pounds and 2 sets of tandem axles, each set transmitting a force of 30,000 pounds.
Am I gonna have to remember what a Class 9 truck is?
No.
There you go.
But don't you, do you not remember what a Class 9 truck is?
I remember Class
It's
9.
the one that's the most common on the highway. So it's the normal Walmart. I'll draw.
The Walmart truck.
The wheels are round.
I do not with square wheels already.
We're obviously not going to let that go.
Look at your notes on that. I'm going to draw the square wheels. My truck is
Just get the trailer with our pickup.
I don't think that's it.
You're missing one next.
We need a horse for that.
Make it target, please don't make it more.
We're all large.
Yeah, this is a little thick right there.
It's because it doesn't have a sleeper.
You don't have to put marker. Put the.
Forgot the trade bar.
This is much better than the car.
TM.
You want to take a picture? I've got it.
No. YouTube is going to be like copyright and it's on the internet.
It's really hard to pick.
This is Walmart's. Okay, so we have a Class 9 truck that has a front single axle, so we've got 10,000 pounds here. Then we have 2 sets of tandems, each set transmitting a force of 30,000. So each group is 30,000 pounds. So we want to figure out what's the total load equivalency factor. Everybody got the truck drawn?
Yeah, it's true. That's where we are. I'm not, I wouldn't give it justice.
I didn't know.
Mine looks really good.
So what's the load equivalency factor for a single axle exerting 10,000 pounds?
0877.
So we just go to the gross axle load of 10,000, go to the single axle column, and that gives us that load equivalency factor. So then we're just going to add for 30,000.
0.658.
So we've got 30,000 and that's spread over a tandem. So you can see if we had a 30,000-pound single axle, that is almost 7 units of damage. But whenever we spread that out over 2 axles, it significantly reduces the impact to the pavement. So that would be, was it 0.685? 658, and then the last one is going to be 0.658 as well. So we just sum those together, and that will give us 1.4. So that gives us the load equivalency factor for the entire truck. Any questions on easels and load equivalency factor? That concludes the transportation review.
Oh, sorry, sir.
Do you have a sign off?
Tune in next week for surveying and